The third speaker is Mr. Jan Krausko.
No, I don't need.
Jan Krausko from Mrs. Grob Aircraft AG from Germany.
Yeah.
The interesting part of his talk that is going to be is we have to take note of the kind of manufacturing process that he is going to talk about. This is very important from the point of view that we have been adopting certain process of manufacture of the UAVs, and his company, they are bringing in a good new process for the low pressure composites, just in time composite prepregs. So we expect to use this type of process in our future systems. So we very much look forward to his talk, which is going to definitely go a long way in making the manufacture easy and also the maintenance that much more cost competitive. Over to you, Mr. Jan Krausko.
So, hello again to all guests. And may I introduce a little bit my company, because we are not such a big company like Saab or IADS. So please have a look on the screen. That is our plant in Germany. We are located south of Germany. I will have a short screenshot where we are exactly located. We have our own airfield with 1,200 meters of length, and that are our production hangars. And here in the middle, you see this one. That is the office of engineering and customer support and everything that you need to produce and then to support the aircraft during the operation. Here you see that are small aircraft what we are manufacturing, that are the G115E. These aircraft are designed for elementary training for air forces, for example. We have delivered up to now 119 aircraft to the Royal Air Force in UK. They are doing the initial training with this aircraft. So let's start with the presentation, and then we will see more information. So, okay. So here you see, first, it's our own high-altitude aircraft, which I will go a little bit more in details through the presentation. So Grob Aircraft was founded in 1971, so 40 years ago, and we were the manufacturer who started with manufacturing of aircraft out of composites. We never produced the aircraft out of metal, so we have already 40 years of experience in composite aircraft. We produced or manufacturer delivered more than 3,500 aircraft, which have flown more than 7 million hours the past 40 years. Most of the aircraft, about 2,500, are gliders and motor gliders, and more than 500 aircraft are training aircraft or engine-powered aircraft. All our aircraft were certified under EASA rules or FAA rules. Before it was LBA, that was the German certification authority. The company was founded by a very known in Germany, very known person, Dr. Grob, who is owning a machining tool company. And they are producing machines for GM, Daimler, and for big companies. That's why we have, when I go to the next slide, sorry, that's now again the location. I forgot that I have this one. So here we see the location, and here that's Munich, and it's about a 1 hour drive with on our highway. So it's about 120 kilometers, but in Germany you can do it also in 45 minutes. I think here it's a little bit longer for this one. So here we see our legacy. That are the gliders which were built until the 80s. Then we switched the late 80s to the training aircraft. We have here the G115E, the G120A, and here at the end it's the G120TP. The first two aircraft are powered by a piston engine, and the last one is a turboprop engine. And as we are discussing about high altitude and UAVs aircraft, we have as well a very good experience in high altitude aircraft. Here what we see is a Strato 2C aircraft, which has a wingspan of 56.5 meters out of carbon composite. And this wing is made out of one piece. So we will go in details in the next slides. So here again, shortly the legacy. So you see from 75 to the 90s, that was most concentrated on gliders and motor gliders or engine-powered gliders. So different kinds of aircraft. We have as well aerobatic aircraft. Then in the 90s, we started with a little bit more differentiated aircraft manufacturing. So we have here the G11A. That is then the GF200. That was a prototype which was flying. It was designed as a business aircraft with a pusher concept. Then here in the middle, we have again a high altitude aircraft, which is designed and he's still flying. This aircraft designed for 54,000 feet and an endurance of about 12 hours. That is the same aircraft with its only trainer, so you can have two pilots in the tandem configuration. Here we see the big aircraft designed for 80,000 feet with the 56 meters of wingspan. The G120A, that is a four-seater prototype aircraft as well. It was flown. We had shot that aircraft here is a turboprop business aircraft, which is as well flown and tested, but went never in production. And we had as well some development in business jet category. So our capabilities, due to the fact that I start here with the high precision metal parts, capabilities of Dr. Grob, of the founder of the company, we have very high capabilities in manufacturing as well metal parts. We have a very high sophisticated metal shop where we are doing our own metal parts like brackets, landing gears with modern CNC machines. Additionally, we are more or less a very high vertical integrated manufacturer. That means that we are doing most of the parts in-house. It has some impacts in the cost, that is sure, but on the other hand, it is an advantage if you want to manufacture or produce or design an aircraft and bring it very fast in a very short time in the air. We are not specialized in avionics or air conditioning our systems. That all these things we are buying from suppliers, but we are integrating by ourselves in our factory. Additionally to the manufacturing of the aircraft, we have as well testing capabilities to certify this aircraft, like a static and fatigue test, ground and flight test, and avionic testing. What is very important for carbon aircraft is as well the lightning protection, as you have no metal parts or no metal sheet. You need somehow a lightning protection, and that is done with the carbon. We have a special first layer what we put on the in the molds, which is where we have implemented or there's implemented filaments of aluminium which are designed to protect the aircraft from lightning, and as well we have some frames and tubes inside of the structure which are designed to the lightning protection. So we have here the composite technology. So it's a proven technology. We are using it for more or less 40 years. That is, I think, a bit known. Oh, sorry, I went too fast, but it doesn't matter. So we see here a small picture of a core. The core can be, for example, honeycomb or foam. Here we have schematics of the carbon fabric. So you have filaments inside, and it's looking like this. That's the role of the fibers are to take the horizontal efforts and as well the vertical momentum, so to augment the stiffness. The core is, for the manufacturing of sandwich parts, is there to increase the stiffness and as well to take some horizontal efforts. The resin is there to put everything together and to fix as well the shape. So we have different techniques of manufacturing composites. So we have, the first thing is a weight layer technique. So you see here mold, and you see the laminate. It's the fabric or the cloth is coming dry to the mold and then is impregnated with the resin manually. Then the same thing that is similar to this is the core. Here you have the shell or whatever part you are manufacturing, and you have two molds where you put, once you have impregnated cloth with resin, you put it in the two molds and then press together and you cure it, where I will go in detail in the next slides. Then we have a Wakem system, so you don't need this upper mold. That is the same principle. You have here the wet laminate, then you have a foil for insulating it, then you have fleece to retrieve the resin what is too much in this laminate, and you have here a vacuum bag where you retrieve the air to have in the fabric only the resin, because air is not holding nothing, so you need some resin inside, otherwise it will not be stiff enough. And then we have the Prepreg technique. It is a little bit schematic and a little bit too easy what I'm showing here, but to show the difference between the Wakem system and the Prepreg technique is that you have the whole mold with the fabric is inside inside autoclave, where you have high temperatures and high pressure. So we have here the layup technique. So what we see is that is an impregnating machine. This machine was co-invented by Dr. Grob, where you have the cloth is here inside of the machine, and it's coming here out, and here inside the machine we apply the resin. I have a short video what I will show you shortly, and here is the next process. Once this fabric is impregnated, we can just call it a just-in-time prepreg, because we are producing this resin impregnated clothes just in time. So only what we need we are putting out of this machine and then applying to the mold. So here you see a fuselage, how it's made. So you see here the impregnated cloth of fabric coming out of this machine, and it is then applied to the mold. And here the same thing, that is the wing. You see the first layer is already there, and this in the middle is the core. So that is, in this case, it's honeycomb, and that is again the cloth what is coming on the top. So you have about two layers. Then you have the core, and then again 2 or 3 years. It depends on the stiffness what you are requiring. So let's show you the video. I hope it's working. Yeah. So here you see the resin with the hardener that is mixed by the machine automatically. It's coming on this foil, and then on the top the dry cloth or the dry fabric is laid on this resin. The resin is already here on this foil, on the blue foil, what you see, and through the capillary forces, it impregnates the dry cloth from the bottom. So, okay, now difference between low pressure and high pressure composites. You see again, here is the mold. Here is the carbon glass fiber sheet, whatever. Then you have here the vacuum foil on the top, and here you have the suction where you retrieve the air and the additional or supplemental resin what is inside of the cloth. The first how we are manufacturing is you have in 2 steps. The first step, you are curing at 60 degrees. That is overnight, about 8 hours, that you have the part cured, pre-cured for the further manufacturing process. And at the end, when all parts are manufactured, put together, we cure at 80 degrees. That is the final curing. So, and we are using this method of composite manufacturing. And the other method, what is very known as well for big manufacturers like Airbus and Boeing, it's the high pressure carbon fiber, where you see that the molds are similar. The only thing what you have additionally is this autoclave, what is on the top, and what is the highest difference is that you have high pressures up to 13 bars and temperatures up to 175. You can go as well higher. It depends on your resin system. This method is as well has its advantages, but for us and as well for we think for UAVs, the method of the low pressure composite is more cost effective because you don't need such high sophisticated parts like for normal aviation like Airbus or for fighter aircraft. So I have here a short overview about the 2 technologies. So as you can see, Grob Aircraft and other small aircraft manufacturers are using this low pressure composite techniques, and here we have high pressure with Eurofighter, Airbus, and Premier One, that is a business jet aviation manufacturer. So there are some differences, but the most important differences are, I think, as well for the UAVs and the small and training aircraft, are here the repairability in the field. So we can easily and quickly repair with a very simple set of tools, and there are no extraordinary investment required. You will see why. I have a short overview of the repair process. And when you have high pressure composites, it becomes a little bit more complicated. You need very sophisticated personnel to do it at once, and as well you need the rivets to repair the surface which is damaged. And sometimes it is a little bit complicated to apply the rivets at some surfaces, so it makes it a little bit cost intensive and time consuming. Why you have to apply rivets on this high pressure composite? Because you cannot restore the original design. That means that if you would like to restore the original design, you would have to put the wing or whatever is damaged in an autoclave and have the 175 degrees and the high pressure. And the opposite, the low pressure composites, there we can restore the original design, the original stiffness. So you have only to apply again the 80 degrees. And how it is done, we will see shortly. Here's a short overview about the curing. So we have here workshop temperature. We are working at 20-25 degrees. Then the first curing is done at about 60 degrees. And then once the parts are trimmed and again assembled or put together with other parts, the last curing is taking at between 80 and 90 degrees. That is coming from the resin system and as well from the certification requirements. But I think that is not the part of this lecture, so that we can maybe discuss beside. So I have here quality assurance. That means that every part what we are curing is monitored by a temperature sensor, humidity sensor, and this is always stored with the parts where we take samples and analyze it as well chemically. So here we see an oven, what we are using. You see here the fuselage, that is the second curing during the manufacturing process. So the first curing had taken when the layer was, the outer skin of the fuselage was laid on the mold, and here you see already the reinforcement that this part, that is the part of the cockpit. So you have here, that is the baggage compartment, here you have then the seats, and here that is the front, the firewall of the aircraft. So that is then more or less every day we are putting parts in the curing room, and the curing room is looking like this. It is 60 degrees, still 60 degrees. So here I have the overview shortly about the aircraft. What I was referring before, that is the egret. You see it's flying. We have still some airplanes flying. They are FAA certified and LBA certified. The wingspan is 33 meters. It is out of two parts. So you see here the one of the fuselage. So it's quite long. So it means 60.5 meters, about 16 meters, one fuselage. And it has achieved an altitude record of 53,000 feet with payload. The payload of this aircraft is about 1 ton, what you could put in this aircraft. Okay. So, and the next most impressive, just the wing. It's a very old picture, so I apologize for it, but you see how it is made. You see no metal parts. Here you have the spar dumps, and here the main, you have two spars, and the fuel here is inside of the wing without integral tank, so it is part of the wing. You have no metal parts for the tank. And as well, you can apply de-ice boots, so it is as well certified for for icing configuration or icing conditions. And here I think that is the most impressive aircraft, and is still parking beside our office. And if you look at the Google Maps, you will see it. It's still there, and if you are staying in front of it, it's very, very impressive, because you have 56 meters where you can look from left to the right to see the wingspan of this aircraft. So it is a maximum takeoff weight of nearly 12 tons. And maximum altitude, designed altitude, was 24,000 meters or 79,000 feet. And it was a governmental founded project which was stopped in the middle of the 90s. And it reached, until it was grounded, nearly 70,000 feet. The endurance was calculated for 48 hours. Here we see the fuselage as well, full carbon fuselage. Here the people working on this, that is the positive mold, which is done before you start with the negative mold. So you see how long it was. And here the most impressive picture, I take the next one. It's here, this one. So you see that are 3 hangars. Each hangar has 30 meters. So in 3 hangars together, we had this wing from here from tip to tip is we have 56.5 meters, and it is still today the longest or the biggest single-piece composite part in the world. There are now some new manufacturers that they are designing a new aircraft which will have probably a longer wing, but for the moment it's the biggest wing what you have. And as you can see as well, the fuel is then installed or stored in the wing, inside of the wing, without metal parts. So here we see, again, an impressive picture for me. That is the test that is a limit load test before flight, and it was all designed in Grob. So we have built as well this hangar only for this aircraft. So this hangar is very tall. It's 60 meters. Where you can park the aircraft, and here you see the limit load test for the wing. So I think the most important thing for UAVs and as well for training aircraft is the repair process. So I would like to start with the repair process, and if we have time, I can as well go through some slides for my manufacturing or production of the aircraft. More? No. Oh, just okay. I will try to squeeze. Okay. So we see here the sandwich repair. You see what you have a damaged surface. So the only thing what you have to do is to apply again the same layers what you had. So let's go a little bit faster through. So what you need for the quick process is co-repair is a few hours. Most of the time what it needed to repair something is that you have to cure it overnight. So 1 night of curing the first time, then you have to repair the skin, and then you have again the curing overnight. So simple process, so not specific equipment is required. Here we have the repair modalities of normal skin, so on a monolithic composite, and as well we have in every our maintenance manuals, for example, the repair scheme and the repair instructions. So every customer, or because we have more or less only fleet customers, so every customer who is maintaining the aircraft can be able or is able to repair most of the damaged areas on the composite side, and for sure as well metallic or engine side, but now I'm talking only about composite, and that is the ability is given. We are offering courses, training course for repair instruction, and then every maintenance facility can more or less repair everything. So here we see short damage. I will go a little bit faster through it. So it was done by a hammer because it's very, very stiff, and to damage it, it's you will not believe it, that it's very hard to damage it. You need a lot of force to do it. So this is done on a wing. That doesn't matter. This hole or also bigger holes is not an issue to repair. So you mark out a large area. You send away the gel coat, and it's looking like that. That's the hole what you have. So you retrieve the honeycomb, what you don't need. That is here. So you see already the surface. You have a hole inside, and now you have to. It's sanded, and it is clean to start with the recovery process. So you have here the honeycomb, and here is cloth for the skin. So you put it inside of the hole. That is a mixture of microballoons and resin. So that is the honeycomb, what is installed. Then you put 3 or 4 layers, depending on the surface, of the carbon fiber. And you cover with the heat blanket, what we had already. And you vacuum out, you retrieve the air, and you cure it during 8 hours. You will now probably ask if it's necessary to put it in the big oven. No, it's not necessary. I will show it to you shortly. It's here. You see we have 2 different methods how to do it. So one is here with this, oops, I am too slow. So here we have a heating plate where you can apply 80 degrees, or we have a heating blower which is heating the air, and this is blown here in this box, and you build around the surface what you want to repair such a box where you can maintain about 80 degrees. That is monitored through thermocouples, and that is so you can repair it everywhere. So you see some damages which are repairable. So you see here the wing tip was damaged. Here we had a hard landing. I go a little bit, maybe bigger surfaces. So you see that it's quite big damage, and I think a metal aircraft to repair and to restore the original design will be very hard to do it in this case. And this aircraft was repaired within 1 month. It was ready to go again in service. So here as well, that was a crosswind landing and damaged the wingtip and more parts. Here's a nose landing, a little bit. It's up to 3G landing. I don't know. So we have again the simple tools. That is for small parts. You can put it in small ovens, or you have these boxes. That was for repair of the wingtips. And here again, the box. It can be in every size what you need, or here this heating plate. So we have efficient process for manufacturing. We can say the requirements for molds are low. All molds are can be handmade, and our molds are all handmade for the moment. You can use CNC machines, but at the end, for duplicating molds, you don't need another CNC machine. You can do the replication of the molds out of the original one. So we have then requirements for ovens are low because the size is defined by the molds, and as well the temperatures are not so high than in the high pressure composites. Cost-effective resin system. Requirements for storage of materials are as well low. We don't need special storage for the composite fabric, because it is not impregnated, so it is a normal dry cloth what you can take and put somewhere where you have about 20-25 degrees. So in the normal production process, they can be stored, and they are not requiring special storage. As well, during the manufacturing process, and as I already mentioned, during the repair process, you don't really need high qualified personnel. It can be all done training on the job. Vacuum bagging is more cost efficient because due to the lower energy requirements, it saves costs. Capital intensive investments are not necessary because a normal vacuum bag is something what is more or less everywhere available, and you don't need the big autoclaves. So a maintenance cost, what is as well very important, what we heard today morning as well, that not only the procurement cost of an aircraft are very important, but as well the life cycle cost, maintenance, support, and as well maintainability and availability of the aircraft. So we can summarize and say that repair costs are low, easy and quick repair. In the field repairability, what is probably as well very important for UAVs, because you never know where they are landing, they get damaged, and you can easily get them very quickly again in the air. So here I have a short overview of the aircraft what we have again, so a little bit bigger picture. So that is the G120TP, that is the A-grade, the high altitude aircraft, 54,000 feet, and that is the 80,000 feet aircraft. So I think my time is over. I have some more, but I can stop here. I had a second one. Okay.
Thank you, Dr. Jan Krausko. He is Director of Operations at the Grob. You might be a little surprised to note that his master's is in economics and bachelor in science. He is presently the Director of Operations. Thank you, Mr. Jan Krausko. He has really given us a great insight into the comparison of the high pressure composites, which require a very high cost of investment, and also repair costs are quite high and requiring 15 bars at 175 degrees centigrade, to the low pressure composites, just in time prepregs, having a low cost of maintenance and ease of field repairs, handling, etc. Thank you very much, Mr. Jan Krausko.